Okay, so we've been, friction's been involved in a bunch of the questions that we've gone over to do in Newton's second law, but we've never really talked about friction for the sake of itself. Okay, what it is, how it works, it's just always there, and it always seems like it's working against us, right? And for the most part, it does work against you. It is a force that generally robs you of energy. Okay? Work is done against it, and it results in a loss of energy, generally. But you'll be able to walk without it. I mean, come on. You know what it's like when the ground gets slippery, right? And if you ever get a chance, watch somebody who's like from a tropical area, when they come here, the first time it gets slippery, because it'll be nonstop laps for a while, okay? Until they get hurt, and then it's not funny anymore. But, okay? But at first, it's gonna be funny, because they have no idea how to walk on a slippery surface, okay? We've all learned it, because as soon as it gets slippery, okay, we walk differently. We're no longer like these powered machines that just push down on the floor and move forward. Okay? We're suddenly we pick up our feet and we set them like straight down on the ground. We don't push forward or backward or side to side because we know there isn't enough friction to support that movement. If I push backwards, that foot is just going to slide out and then I'm going to flop down on my face. Okay? Or I'm going to go the other way. Okay? I'm going to land on the back of my head. Right? So we understand that. We know that the best way to maintain the most friction is to put the most weight right on top. Okay? Because friction is related to how hard the two surfaces are pushed together. Okay? The harder they're pushed together, the more friction there's going to be. Think about this. If I want to move this desk, but I don't want to pick it up and carry it, I just kind of want to slide it along the floor. What's the best way to do that? Okay, which one do you suppose? Like, if I push it, so I get like this, and I start pushing, it doesn't work very well. There's less friction on my feet, okay? I'm sliding backwards, it doesn't work at all. Why was that so much easier?
Because you have more friction on your feet because your feet are more extended.
Okay, partly because I have better grip, but what did I do with the desk? Like, this is harder. I'm pushing it. I'm fine friction-wise, but this is harder than when I did this.
Is it because the angle is not, most of your force is going that way and not into the floor?
It does sort of have to do with that. Okay, sorry, go ahead.
Is it because it's moving to your center of gravity? Or your
No, that has nothing to do with my center of gravity.
You're taking weight off the desk and you're creating less friction while pulling it back.
Exactly. When I pull it, I lift up some of the desk's weight. I take that weight off the floor. Now there's less force between the desk and the floor. Right? The normal force is less. The weight of the desk is still the same, but not all of the desk's weight is on the floor now. I'm holding some of it. So the floor doesn't have to push as hard, and there's less friction. When I put this thing on the floor and push on it, there's even more force than when it's just sitting here without me bothering it. Right? I push down into the floor, and according to Newton's third law, which we haven't really talked about yet, the floor has to push back even harder. Well, that makes even more friction. Okay? It makes no sense to move a desk this way. It's highly inefficient because I'm increasing the amount of friction. All right? We just got our first snowfall on the weekend. Things got a little hairy out there, a little bit slippery. Okay? Probably most of us are looking, or maybe we've already done, get our winter tires put on. Okay? Or if you drive a pickup truck, what do you sometimes throw in the back? Sandbags, hay bales, anything that, a couple cinder blocks, something. Why does that work?
Reduces the weight, so it reduces the friction.
Yeah. The more weight you have over those back wheels, the harder the ground has to push back against your tires, which increases the force of friction. Okay? It's otherwise quite inefficient to add weight to your vehicle, Okay, now you have to move more weight. It's going to reduce your fuel efficiency, but it's going to increase your traction. Okay, heavier vehicles generally have more traction because there's more friction on a heavier vehicle. Okay, all things considered. Now, what is changing your tires? Like we go to winter tires here. Why are winter tires better in the winter than summer tires? Besides the fact they're obviously called winter tires. Some of you were thinking that.
Is it because like the rubber's more soft, so that it like absorbs more wear out?
Yes, the rubber compounds that winter tires are made out of are softer. They remain pliable, okay? That means they can kind of take the shape of the ground, okay? Better at colder temperatures. In fact, 4 degrees Celsius and lower, you should have winter tires on, okay? All season tires actually get quite hard below 4 degrees Celsius, and that reduces their ability to have good traction, okay? So winter tires are obviously better for cold temperatures because they're softer. Now, that means they're terrible in the summer. Does it? They're actually not bad in the summer. They just wear really fast, okay? Because they're very soft, okay? And if it's warm, they're even more pliable and softer, and so they wear out a lot faster, okay? So if you keep your winter tires on all year round, know that like for 6 months of the, okay, what are we getting, 4 months of the year, okay, you're really wearing them out quicker, okay? And you don't want to do that. So once the temperature is going to consistently be above freezing, you should probably get them taken off, okay? 'Cause some people get them put on like super early, and like this year, if you got them put on in early October, you probably wore them out quite a bit because it was quite warm through October, unseasonably warm. And so you probably caused a lot more wear than you would normally cause at that time of the year. So there's a couple of things that affect the force of friction. On your formula sheet is this formula here. The force of friction can be calculated by multiplying mu times the normal force. Okay? So the normal force is how hard the surfaces are pushed together. Okay? Mu is the coefficient of friction. Mu is different for every combination of surfaces. Okay? The mu between an ice cube and a Teflon pan would be incredibly small. The mu between rubber and asphalt would be incredibly high. Those are two very high friction surfaces. Sandpaper on wood would be a high mu situation. Okay? Any place where friction is high, mu is big. Anywhere where it's very slippery, mu is very small. Does that sort of make sense? Okay. The other thing we need to understand is that there's 2 types of friction. Static friction and kinetic friction. Formula doesn't change. We just have to understand which one is going on because there's actually mu's for static and mu's for kinetic. You will never be required to memorize any of them, okay? Now, static friction is what happens when the surfaces don't slide past each other. Okay, so when I was pushing on the desk and the desk wasn't sliding, it's because I couldn't overcome the force of static friction between the desk and the floor. Once I did this, that's kinetic friction. Okay? Kinetic friction is always less. Once you get something going, once you overcome friction, it's much easier to keep it going because kinetic friction is always less than static friction. Okay? This is why we have all-wheel drive and traction control systems on our vehicles. Okay? If we spin the tires, that's less effective at propelling us forward than not spinning the tires. Okay? I mean, you guys have all seen people trying to get out of the parking lot when it gets icy, right? And it's the people that don't spin their tires that actually get out better, right? There's been people who have gotten on that hill, tires spinning, and they're actually sliding backwards. Don't ever get too close to the person in front of you on that hill, okay? Because it has happened where someone has spun the tires so badly that their kinetic friction allowed them to go backwards. Even though the tires were spinning forwards, they slid down the hill, right? So we want to be mindful of that. If we can keep our tires from spinning, we're going to get maximum use out of the friction we have. okay? That's why something like a, you know, like a Tesla, for example, that has computerized traction control is so quick to accelerate. It doesn't waste any energy using kinetic friction, okay? If a wheel starts to slip, power is automatically diverted away from that wheel to a wheel that grips. Okay, and that's what limited slip differentials and traction control do. They divert power from a wheel that is slipping so that it can regain traction, and they send it to a wheel that has traction. Okay, and that will maximize your forward force and allow you to accelerate best. If you just, you know, throw it in first, floor it, and dump the clutch, you're just going to like burn off hundreds of dollars worth of tire. Okay, now in an impressive fashion, of course, because it's going to be, you know, tire smoking.
I just have
Okay, yeah, so you're just gonna have all this kinetic friction that's really not gonna result in a lot of force forwards. Okay, so there's the two different kinds, right? If you're going around a corner and it's icy, once you start to slide, you're pretty cooked. Okay, because that's no longer static friction, it's kinetic friction, and you're not likely to regain the static friction you once had. Okay, you have to find a way to, you know, not have those wheels cranked right over. You gotta do what's counterintuitive, which is turn into it, okay? And so you can hopefully regain some static friction and make the turn afterwards. We talked about Canada's first driver, right?
Yeah.
Yeah, okay, that's that test that they always do. Yeah, the styrofoam blocks go flying everywhere. Whatever beautiful car they start with is a complete mess by the end. It's tragic. Okay. All right, everybody good with the two kinds of friction? Okay. All right, so this person here is doing that thing that I was doing before, okay? The least efficient way to move a desk, okay? The way that makes no sense from a common sense perspective, to push downwards on a desk to make it go forward, right? That doesn't make much sense, because what we're doing here is, yes, she's exerting a force this way, right? That has a horizontal component, but also has a vertical component. So if I'm drawing a free body diagram for that desk, okay, I've got gravity, I've got that downward component, okay, so force vertical, okay, and then I've got this force horizontal, and then I've got force of friction backwards, okay, but the force normal is what affects this. And the normal force has to balance these two things because the desk isn't moving which way? It's not moving vertically. So that means that the vertical net force is 0. So my normal force is actually Fv plus Fg. It's really big in that situation. And because our formula for friction is mu times the normal force, anything that increases the normal force is going to increase the amount of friction that's present, including pushing downwards on the desk to move it forwards. Okay? This is also then why, when I lifted the desk, okay, and pulled at an angle like this, I got a better deal. Okay? I still had a horizontal component, but now the vertical component is which way? Up. So now if I'm looking at that free body diagram, I got force of gravity and force vertical, and they almost cancel each other out. So my normal force now is really small, okay? Because I'm exerting some force upwards that takes some of that weight away. The net force vertically is still 0, right? The desk isn't moving vertically, right? But I've reduced the amount of weight that's now on the floor. Okay? Everybody all right with that? This is why rocks in curling are heavy. Okay? If the rocks in curling were really light, it would be a lot harder because they wouldn't stop. Okay? There'd be less friction between them and the ice, and it would just keep going. The ice would either have to be 4 times longer, or you'd have to like just give them a little nudge and hope they would stop before they got to the other end. Okay?
why they are.
in fact, so heavy. Is that making sense? All right, so static friction, okay, can actually change. The amount of static friction is not a fixed value, and here's why. If we go back to my desk example here, okay, if I just push down a little bit, okay, the force of static friction isn't very big, but it's also still not enough, I'm still not pushing hard enough to move the desk. The harder I push, what happens to friction? The greater it gets, okay? So there isn't a fixed amount of static friction between this object and the floor. It's completely dependent on how hard the two surfaces are being pushed together. And eventually, I'll push hard enough, hopefully, that I overcome it and the desk gets to move. Okay, but it can change. Okay. Yeah. So we already talked about that one. Okay. So this is what we were talking about here. So let's actually have you guys write this one down and let's calculate the force of static friction, okay, on this desk here. Okay. It's going to be a Newton's second law thing, not a mu times normal force thing necessarily here. What is the key? What do I have to remember about any situation involving static friction? What's the object not, what are the surfaces not doing? Not sliding, which means the object's not moving, which means the net force is, okay? So if we've got a static friction situation, okay, the net force has to be zero because there's nothing moving. Okay, the two surfaces are not sliding past one another. Okay, so in this question, they're saying the desk remains stationary and this force here is 165 newtons. So how do I go about calculating the force of static friction in this question?
Sin 30 times 165.
Sine or cos? Cos, yeah, okay? So here's what I have to realize. This is a downward force, it's pushing into the floor, okay, but the desk isn't moving. So that means, since the desk can only move horizontally, that the force of friction has to equal the horizontal component of that 165 newtons. That's why the desk isn't moving. The desk isn't moving vertically, nor is it moving horizontally. Okay? So that means the net forces in all directions are zero. Okay? But this is the one we're concerned with. So if I go F horizontal equals negative the force of friction, okay, then I can calculate F horizontal by simply going the cos of 160, or sorry, the cos of 30 times 165. Okay, I'm calculating the horizontal component of that applied force, okay, knowing that it's equal to the force of static friction because the desk isn't moving. What do we get when we do that? My calculator's still firing up.
143.
Okay, so the force of static friction is negative 143 newtons. Okay. Everybody all right with that?
If we said like 143 newtons, so.
Backwards?
Let's do it.
Totally fine, yeah. Yeah, because they really didn't say much. They didn't say forwards, they said below, and they just said theta's 30 degrees. They didn't even say below the horizontal, so we could kind of get away with anything. Be south for all we know. Okay. calculate for me the force of friction in this question. I place the 10 kg block on a 20-degree incline and it doesn't move. Okay, what two forces are equal in this question?
Parallel force and friction.
The force parallel and the force of friction. They have to be equal here, otherwise the box would slide down the ramp. Okay, the fact that they are equal says that's why it's stuck to the ramp, because F parallel isn't bigger than the force of static friction. Okay, what if it was sliding down the ramp at a constant velocity? They'd still be the same, except it wouldn't be static friction, it would be kinetic friction. Okay, still the same situation. All right, so as long as I can recognize that F parallel and the force of friction are equal here, okay, and that it's static friction, I can go about calculating F parallel in the same way we always do. Okay, Fg, okay, F normal, F parallel, okay, 20 degrees, so this is going to be 98.1 newtons, and then F parallel will be the sine of 20 times 98.1. Alright, so 33.55 newtons. We only had two significant digits in that question, so 34. Up there. Everybody okay with that? Alright, now here's the next thing. What is the coefficient of friction between the box and the ramp? Okay, so we haven't done one like this, so I'm just going to remind you. The formula for force of friction is mu, which is the coefficient of friction, how sticky the two surfaces are, okay, times the normal force. Have we ever had to calculate normal force on an inclined plane? Not yet. Is it hard? No, it's just straight, okay? We've been calculating F parallel being the opposite side by going sine of 20. How do I get F normal? Cos of 20. Okay. All right, so now I can get the normal force, and I'll just go cos of 20 times 98. Whoop, 98. One. Okay, so my normal force is 92.18 newtons. Okay, so if I want to get mu, all I have to do is take normal force over here. Right, so I'll take my force of friction, which was 34 newtons, and divide it by 92.81. Sorry, 92.18. And that will give me mu. So the coefficient of friction there is 0.37. What are my units for that? None. Why are there no units?
Dividing newtons by newtons.
Exactly. I divided the force of friction by the normal force, and the units for both of those are newtons. Newtons divided by newtons is 1. So there are no units for the coefficient of friction. It is a coefficient. It is the ratio, essentially, between force of friction and normal force. And it is most often less than 1. Okay? There are some rare circumstances where your coefficient of friction can be more than 1. Okay? But most of the time it is a decimal. Because most of the time the force of friction is less than the normal force. All right, so this is the situation that we hadn't encountered yet, that I had talked about a little bit when we were doing all those inclined plane questions. We don't ever have to calculate the normal force. We're not going to need the normal force. Well, now we might. Now an inclined plane question could just as easily say something like, a 10-kilogram block is placed on a ramp and it's sliding down with this acceleration. Calculate the coefficient of friction. okay? Or I could say calculate the acceleration knowing the coefficient of friction between these surfaces is this much, and then you'd have to calculate the force of friction using that instead, okay? It doesn't really change what we do, it's just one more way to calculate the force of friction. Okay? All right, like this question. So give this one a try. The coefficient of friction between the 20 kilogram box and the ramp is 0.125. It is being pulled up the ramp by a force of 120 newtons. Calculate the acceleration of that box. Okay. Let's complete the free body diagram here first. If I'm looking at just forces acting along the plane, what are those two forces?
The force parallel and the force of friction.
Right, one of them is F parallel, likely the bigger of the two, okay? And one is the force of friction, because it's being pushed up the ramp, and friction always acts in the opposite direction. Now, if I want to get the acceleration of the box, I need the net force, okay? And F net is going to be F applied plus F parallel plus the force of friction. And I only know F applied right now, 120 newtons up the ramp. So I've got to calculate the other two. Luckily, I can calculate the other two, one directly using the triangle inside and the other using one of the sides of the triangle. Okay, so this is 25 degrees here. So this will be 196.2 newtons, okay, 20 times 9.81. And then I got to calculate my other sides. So F parallel, okay, will be the sine of 25 times 196.2. Okay, so 82.92 newtons. And I got to calculate normal force so that I can get which force? Force of friction. Okay, so cos of 25 times 196.2, 177.82. All right, now I can calculate the force of friction, okay, because it's mu 0.125 times 177.82. Okay, mu times the normal force. So, all right, so we get 22.23 newtons. All right, now I've got the parts of my sum of all forces. So now I can put them together. All right, I have 120 minus 82.92 minus 22.23. I mean, strictly speaking, I should say plus negative, but it's the same thing mathematically, right? And so if I do that, all right, so my net force is 14.85 or 14.86 newtons. Up the ramp, so my acceleration will be F net over m. So my acceleration should be 0.74 meters per second squared up the ramp. Everybody all right with that? Okay. Does this change any of the Newton's second law stuff we do? I mean, that's a pretty straightforward inclined plane question. Just an extra step in it. We had to calculate the force of friction using our new formula. And that's the extent to which friction's really going to come into play for anything. It's just an added thing that we got to watch for. Okay. All right, we did one like that already, so we'll skip that one. I would like you guys to try question number 2. We haven't done one like that. That's a tricky one. Okay. What's the key thing we need to understand here?
It's static friction, so your net force is.
Right. It's static friction. My net force is 0. That means the force of friction and what force have to be equal? Right. F parallel. Okay. So we know then that this force up being 4.4 times 10 to the minus 2 is what F parallel is at its maximum amount. Because any bigger than that, and it would slide. Okay, does that help me get the angle now that I know F parallel? Give it another couple minutes. Okay, so once we know what F parallel is, okay, we can get the angle because we know the mass, so we can get FG, and knowing F parallel would then mean we would have 2 sides of the triangle and could thus calculate the angle between them, and that's the angle of incline. Right, so we just have to calculate what FG is. So 0.007 times 9.81. Okay, that gives me FG. I already know what F parallel is. So now I can say that the sine of theta equals F parallel divided by FG, which means that theta equals sine to the minus 1 of F parallel over FG. So inverse sine of 4.4 e negative 2 divided by that number here. That gives me 39.8 degrees above the horizontal, or below the horizontal if it's the angle of decline. Right, so are there lots of like really subtle pieces of information in a question like that? Okay, the most subtle piece of information in that question is it's not moving. Okay, I told you it's static friction. Right? From that you have to go, oh right, so that means this force is equal to that force, and now I can go and do this. Okay, there's just, you have to have a really good understanding of how all these things work to figure out those pieces. All right, now, direction of kinetic friction on an incline. So if it's kinetic friction, what's the object doing? Moving. All right, so it's sliding. So direction of kinetic friction on an incline is always which way? Working against. Yeah, always opposite. Whatever direction the object is sliding. So if I'm sliding it up the ramp, friction is down the ramp. If it's sliding down the ramp, friction is up the ramp. Kinetic friction is always opposite. Okay? And in that way, kinetic friction on an incline is kind of always opposite F parallel. Right? The tendency would be for it to go down the ramp, but because it's not, it's opposing. Okay, static friction would have to be up the ramp in that case. Okay? Now, what if I was pushing something up a ramp, but I couldn't actually make it move up the ramp? Then which way would static friction be acting?
Down. One pushing and friction with 2, right?
If you can't move it, it would still be acting
It would,
against you.
it would still be, I would say it would still be acting against me, yeah. Okay? If I'm trying to push it up the ramp but I can't, okay, it's some combination of F parallel and the force of static friction working against me in that case. Now, I would have to hope in that case that if I let it go, it also wouldn't come crashing down the ramp at me. Okay, that's kind of the weird part of that, right? Would it move if you let it go? I don't know, right? All right, so we talked about accelerating down an incline because we just did a problem like that, and we did a problem like that already. And we've done one like that already. Okay, let's give that one a try. So we got a 40-degree incline, okay, and we just set the block on there. Nobody's pushing the block. Okay, the block has just been set on the incline. We know the coefficient of friction. What's the acceleration? Easy question. So for this one, okay, we got a 40-degree incline, okay, and it's 20 kilograms. And we know that the coefficient of friction is 0.185. All right. There's only two forces that are causing the movement: F parallel and the force of friction. I would have to assume that F parallel is smaller than the force of friction, okay, because it's asking what the acceleration is, and it doesn't say anything is pushing it up the ramp, so it's got to be sliding down the ramp, right? So I can calculate both of those forces because I know the mass and I know the angle. Okay, so this is going to be 196.2, and we have F normal over there. And don't confuse F normal and F net; they're different. Okay, Fn is F normal. All right, so I got to calculate F parallel. Right, so F parallel will be the sine of 40 times 196.2. So 126.11 newtons down the hill. Okay, so 126.11 newtons. And then I got to get the force normal so I can get the force of friction. So that'll be the cos of 40 times 196.2. So 150.30. And now I can get the force of friction because it'll be mu 0.185 times 150.3. All right, so there's my force of friction, 27.81 newtons up there.
Is F parallel always down?
Always, because it's the vector sum of normal and gravity. It can only go down the ramp, right?
So how do you know that force of friction is going up or not?
Well, because it doesn't mention anything about it moving up the ramp, right? It's just saying it's on the ramp, which says it's sliding. It's either not moving or sliding, because there's no mention of it being pushed or pulled up.
Okay.
Yeah, so I kind of have to make an assumption on that one. Okay, so now I've got my force of friction, and I've got my F parallel, so now I can calculate F net, and this becomes just like every other Newton's second law problem. So 126.11 minus 27.81. All right, so my net force is 98.3 newtons down the ramp. Okay, and so now I can calculate the acceleration by going F net over m, so that 98.3 divided by 20. And 4.9, I'm gonna have two sig digs there, so 4.9 meters per second squared down the ramp. Okay, so as I was saying, friction just adds, like just knowing this formula for force of friction just adds in that, all right, well there's one more force we might have to calculate as opposed to just be told. Okay, but other than that, it just works into any Newton's second law problem like any other force does. All right, so just to give you an idea here, some of these coefficients of friction, right? And there's obviously static on the left and kinetic on the right, okay? Copper on copper, so copper for whatever reason is a very high friction material, especially if it's against itself. Okay, so like trying to slide, if you actually had copper pennies, trying to slide them past each other, okay, would be a high friction situation. Coefficient of static friction is over 1, significantly over 1 in fact. Okay, so there's a lot of friction there. Steel on dry steel, so if I had 2 pieces of steel and I was trying to slide them past each other, coefficient of friction would be 0.41. That's why you don't want to run your car without oil in it, because that would be steel on steel, and that will destroy your car. Okay? At some point, the heat produced will cause the rings and the pistons to expand, and the crank will break and go through the cylinder wall, and oil will spill everywhere, signifying the death of your engine. Okay? So if the oil light comes on, stop. Turn off the car. Okay? You need to have something checked. Okay, steel on greased steel. Dude, that makes a big difference. Okay, as soon as you grease it, it's considerably less friction. There's still friction, that's why engines wear out. Okay, but there's a lot less of it. Okay, dry oak on dry oak. So I don't know why you'd be sliding those 2 things past each other, but okay, there's a fair amount of friction between those. Okay, a rubber tire on dry asphalt. Right, look at the difference. Once you start that tire spinning, you lose 1/3 of the friction there. Okay, it's a lot. It's a lot less effective if it's spinning. Rubber tire on wet asphalt. As soon as it gets wet, half as much friction as there was before. Okay, rubber tire on dry concrete, 1.0. Okay, that's why asphalt is superior in terms of traction to concrete. Okay, so why in California do they use concrete instead of asphalt?
Something with heat.
Yeah. If you've ever seen what asphalt does in the extreme heat, it softens. It even happens here. Okay? In the summertime, big heavy trucks will create those grooves. And if you ever been stopped at the stoplights in the city, okay, but there's like big dips. Okay, in the summertime, asphalt gets soft in the sun, and weight can cause it to compact. Okay? I remember as a kid, we got a flat tire, and my dad got out to change it. We were driving down to Disneyland, so we were in California, and it was really, really hot. He started jacking up the truck, and the jack sank. Like he couldn't get the tire off the ground because the jack kept sinking into the asphalt. Okay, so it gets really hot. Okay? If you ever watch that death race, okay, that they do the running race through Death Valley, okay, all the runners, they run on the white line on the road, or their shoes melt. Okay, so if you see them running the death race, they run like this. You can stay on the white line on the highway so that their shoes don't, because the white line is cooler than the rest of the road. Okay, rubber tire on ice. Oh, that's a small number. Okay, that's why it's so hard to get going, or stop, or turn, or any other way maneuver your car. Okay, when it gets icy. Okay, curling stone on ice, also pretty low coefficient of friction. Teflon on Teflon, pretty low. Okay, and then wax skis. So if you have like cross-country skis, you put different kinds of wax on them, especially if they're like old-fashioned ones that are actually made of hickory and not plastic. Okay, they would put different types of wax on for different temperatures, and different types of wax for even different types of snow. Okay, whether it's fresh snow or old snow or wet snow or dry snow, you use a different wax. There's like 10 different waxes you have to get for cross-country skis, unless you get the waxless kind. But apparently they don't work as good. Okay. Synovial fluid on your joints. Okay, so you guys are young, you still have this stuff inside your joints. Okay, and it's the thing that lubricates the joints and keeps them from cracking and grinding and all the awful things mine do. Okay, when I move. Right. So synovial fluid is pretty low friction. Right? So you want to have it in there. You want to have it in there so bad that now when I'm old, I actually get it injected into my knee. So they take this needle that's like this long, and big, and they jam it into my knee, and it just whoops down there. Okay? And it's also got like cortisone and hyaluronic acid and all kinds of other good things that make my knees feel way younger. Okay, but synovial fluid is really good. You don't want to lose that stuff because it really helps your joints. Okay. All right. tires. Okay, this was the thing I wanted to talk about. All right. In terms of tires, why do sports cars have really wide tires? Have you ever noticed like on a really high-end sports car, especially the back tires are like really, really wide, okay? But on most cars, they're not.
To like increase the amount of like area the tire has on the ground.
Okay, does surface area affect friction?
Probably.
Everybody nods their head yes when I ask that, because otherwise, why would tires be wider, right? Like it's a common sense answer. The problem is that it's not what you think. Surface area isn't part of that formula. All that's part of that formula is normal force and the coefficient of friction. So why does tire width make a difference? Because it does, okay? Otherwise we wouldn't do it. Why does the width of a tire help with friction?
The force is being distributed over a larger area.
And again, that's what we would think, except that it has nothing to do with the forces. It has to do with mu. If you have a larger surface area, it doesn't increase the normal force. What it does is when your tire is spinning, a wider surface area helps to dissipate the heat better than a small surface area, which can hold the integrity of the rubber longer. If you have a narrow tire, it'll burn off faster than a wide tire because there's less of it exposed to the air to dissipate the heat. So it will vulcanize, that is liquefy and then burn, okay, faster than a wider tire does. So it retains the integrity of the rubber, which affects this. Because once the rubber starts to burn, mu goes down, okay, because now it's no longer rubber, it's like a liquid, okay, and mu decreases significantly. Right? That's why tires typically, unless you're on a drag racer that would have slicks, have grooves, have some kind of pattern, tread pattern on there. Okay? That allows for the circulation of air. It also allows for the pumping of water, like so you don't hydroplane. Treads help with that. Okay, on a winter tire, all those little sipes. I don't know if you guys have noticed this, but on your winter tires, there's way more grooves in a winter tire. Okay? Each one of those little, especially the really small grooves. Okay? So if you look at like a winter tire, okay, you've got big channels. Okay? And then on those channels are blocks. And inside those blocks are tiny little like squiggly lines called sipes. Okay? What those sipes do, and this is part of the reason why winter tires are better, because they're softer, okay? When those come into contact with the ground, they open up slightly. And that pulls water into the sipe. So if your tire is spinning, this will pull the water that's produced from melting the ice up into the tire and away from the interface between the rubber and the ice. Because it's all the water does is act as a what? That's a lubricant. Okay? So you want to pull that water away from the contact surface so that you're not hydroplaning. Okay? Because if you're spinning the tires, you're melting the ice and turning it into water, and now you're hydroplaning in addition to spinning your tires. So these little sipes will pull that water away to maintain the traction, okay, between the tire and the ice. It's why your winter tires have way more grooves on them than summer tires do. Summer tires don't need that. They just squish the water up to the sides with their tread pattern. Okay? Winter tires have this extra ability that summer tires do not. All right. All right, now, this is the creme de la creme of friction questions. I always have a question like this on the unit exam. All right, so I would write it down and give it a try. It's friction, it's vectors, it's Newton's second law, it's a little bit of all the fun stuff, except in climate. Doesn't have any. For this one here, because it didn't have a vector on it, sorry, I was thinking that this was the one that had the angled force on it. So this one's a bit simpler because we're looking for the acceleration of the box. We're told it's being pulled by a force of 200 newtons. Okay? There would be a force of gravity here of 196.2 newtons. What's my normal force?
The opposite of that.
Right, 196.2 newtons, up. Okay, because it's a level surface and there's no angled force here. And so F normal and force of gravity are equal in this situation. So I just have to calculate the force of friction. And I can do that because they told me the coefficient of friction over there. Right, so force of friction is mu times normal force. So 0.8 times 196.2. That gives me 156.96. All right, can I calculate my net force now?
Yes.
Yes. Okay, so I calculate my net force, just subtract those two numbers and divide by the mass of the box, and I'd have my acceleration. So 200 minus that number divided by 20, 2.2, right? We have, yeah, only two significant digits, so 2.2 meters per second squared forward. Now, how does this change if this happens? Okay, so now it's kind of like what I did at the beginning of class. I pick up this desk and now the desk is angled and I start pulling. Am I pulling forward? At an angle. Some of my force is forward, but some of my force is upward because I'm pulling at an angle. The force I exert on this desk when I pull it is angled at about 20 degrees above the horizontal. Okay? Does the desk move vertically? No, it still moves horizontally, which means that my net force up and down is still what?
Zero.
Right. But now added into that are the vector components of my pulling force. There's a vertical force that's acting up and a horizontal force that's acting forwards. So what I would have to remember if this was the situation is that Fg plus F normal plus Fv still equals 0. Right? Because then what that's going to do is it's going to change how much friction there is. That's why it was so much easier for me to pull the desk that way. Okay? By pulling it at an angle, I reduce this force because some of Fg is being taken care of by me. Okay? Does that make sense? Right? So that would change it. I just have to calculate my vertical and horizontal components and understand that they play a part. All right? Okay, you will have a quiz tomorrow at the start of class, and then we will get into your Newton assignment. Okay, and you'll have the class to work on that tomorrow.
And